On November 16th, 1974, humanity sent its first serious postcard to the stars. From the Arecibo Observatory in Puerto Rico, a 3-minute broadcast was aimed at M13, a globular star cluster 25,000 light-years away. The message, devised by Frank Drake and Carl Sagan, was a simple digital pictogram. It contained 1,679 bits. It showed our number system, the atomic numbers of key elements, the formula for our DNA, a stick figure of a human, and our solar system. It was an act of profound optimism. A greeting card to the cosmos. That same year, British astronomer Sir Martin Ryle received the Nobel Prize in Physics. He was a pioneer of radio astronomy and the Astronomer Royal of the United Kingdom, but he did not share Sagan's optimism. Ryle publicly warned against any and all attempts to signal our existence to the void. He argued that any civilization we contact would, by necessity of interstellar travel, be vastly older and more powerful than our own. He believed the outcome of such contact would not be a friendly exchange of knowledge. He believed it would likely be hostile. He saw our cosmic postcard not as a greeting, but as a scream in a dark, unknown forest. He feared that we were revealing our location to potential predators, and that the long silence from the stars was not an invitation, but a warning. The debate he started in 1974 has never ended. It hangs over every radio dish pointed at the sky. It forces us to ask what, or who, we are really looking for. And it is the first of many questions the universe demands we answer. Number 20. Our search for aliens is a dangerous gamble. The Arecibo message of 1974 will not reach its destination for another 25,000 years. The odds of any civilization being there to receive it in that exact spot at that exact time are infinitesimally small. On August 15th, 1977, a radio telescope at Ohio State University picked up a powerful, narrow band signal lasting 72 seconds. It came from the direction of the constellation Sagittarius. The signal was so striking that astronomer Jerry Eman circled it on the printout and wrote "Wow" beside it. The "Wow" signal has never been detected again. It is the most compelling candidate for an extraterrestrial broadcast we have ever found. We have been actively listening for alien signals for over 60 years. In that time, we have surveyed less than 1/1,000,000,000th of the cosmic haystack. Our efforts to contact other life forms are based on a huge assumption. We assume that anyone out there is friendly, or at least curious and peaceful. This is the foundation of projects like METI or Messaging Extraterrestrial Intelligence. It is the continuation of Sagan's dream, but this assumption is not based on evidence. It is based on hope. We project our own best qualities onto the unknown. We want to find enlightened explorers, wise teachers, fellow travelers in the cosmic dark. But the universe does not operate on hope. The history of life on Earth is a history of competition. When two civilizations have met on our own planet, the one with the more advanced technology has almost always dominated, displaced, or destroyed the other. This is a pattern repeated across continents and millennia. Why would we expect interactions on a cosmic scale to be any different? A civilization capable of crossing the vast distances between stars would have technology that seems like magic to us. Their energy production would dwarf our entire global output. Their understanding of physics could allow them to manipulate matter and energy in ways we cannot even conceive. Compared to them, we would be like ants on a sidewalk. An advanced civilization might not be malicious. They might simply be indifferent. If they need resources, they might take them without a second thought for the primitive life forms that happen to be in their way. Our planet, our sun, our entire solar system could be just a convenient source of raw materials. They might not hate us, they might not even notice us in any meaningful way. Our extinction could be a footnote in an industrial process. This is the Dark Forest Theory, a chilling answer to the Fermi Paradox. The paradox asks, if the universe is so big and old, where is everybody? The dark forest answer is that everyone is hiding. The universe is a dark forest, and every civilization is a hunter. In this forest, you cannot know the intentions of any other hunter you encounter. You do not know if they are hostile or friendly. The safest course of action is always to eliminate any other life form you find before it eliminates you. To reveal your existence is to invite your own destruction. In this scenario, the silence of the cosmos is not a sign that we are alone. It is a sign that everyone else is smart enough to keep quiet. We are not keeping quiet. We are broadcasting. Our television shows, our radio signals, our radar systems have been leaking into space for nearly a century. These signals are very weak, and they degrade quickly over distance. But they are out there. An expanding bubble of noise announcing our presence. Projects like METI want to go further. They want to send powerful, targeted messages like the Arecibo broadcast, but much stronger and more frequent. They believe the potential reward, the knowledge and perspective gained from a successful contact, outweighs the risk. Sir Martin Ryle disagreed. He saw it as a reckless bet with the fate of our entire species. The proponents of METI argue that any civilization capable of reaching us would already know we are here from our passive leakage. They argue that a truly advanced civilization would have transcended predatory instincts. But this is just more hope. We have no data to support this. We are basing the survival of our world on a guess about alien psychology. The gamble is this: we might gain unimaginable knowledge, or we might trigger our own extinction. The stakes could not be higher, and we do not know the odds. Every time we send a deliberate message, we are rolling the dice. We do not know what kind of universe we live in. We are hoping for an invitation to a party. So we might be sending an invitation to our own funeral. Number 19, the silence of the universe is itself an answer. Our galaxy, the Milky Way, contains an estimated 400 billion stars. The observable universe contains an estimated 2 trillion galaxies. Many of these stars have planets. The Kepler Space Telescope found that small, rocky planets in the habitable zone of their stars are common. There could be tens of billions of Earth-like worlds in our galaxy alone. Our sun is a relatively young star. It formed about 4.6 billion years ago. The universe is 13.8 billion years old. Billions of Earth-like planets have existed for billions of years longer than our own. Given these numbers, the universe should be teeming with life, and not just simple life. There has been more than enough time for countless civilizations to arise, develop technology, and spread across the galaxy. In a few million years, a single civilization with advanced space travel could colonize the entire Milky Way. A million years is a cosmic blink. So where is everybody? This question was famously asked by physicist Enrico Fermi in 1950. It is called the Fermi Paradox, the staggering probability of alien life clashes with the complete lack of evidence for it. The silence is our only hard data point, and it might be telling us something. There are many possible explanations for this great silence. Each one has profound implications for our own future. One possibility is the rare Earth hypothesis. This idea suggests that while planets may be common, the specific conditions that led to intelligent life on Earth are incredibly rare. It required a stable star of the right size, a large moon to stabilize our axial tilt, a magnetic field to shield us from radiation, plate tectonics to regulate carbon, a gas giant like Jupiter to sweep away killer asteroids, and 1,000 other lucky coincidences. Maybe the emergence of complex life is not a common event. Maybe it is a near impossible lottery, and we are the only winners in this cosmic neighborhood. This would make us precious, but also terribly alone. Another possibility is that intelligent life is common, but it inevitably destroys itself. This is the Great Filter Theory. The theory proposes that there is some step in the development of life that is almost impossible to overcome. This filter could be behind us, or it could be ahead of us. If the filter is behind us, it might be the leap from non-life to life, or from single-celled organisms to complex animals. In this case, we have passed the great test. We are one of the few who made it through. But if the great filter is ahead of us, then the silence is a terrible omen. It would mean that every civilization that reaches our current level of technology ends up destroying itself through nuclear war, climate change, engineered plagues, or some other danger we have not yet discovered. The silence from the stars would be the silence of a cosmic graveyard. Perhaps civilizations exist, but interstellar travel is simply too hard. The distances are too vast, the energy requirements too great. Maybe every civilization is trapped in its own solar system like we are. They might be broadcasting signals, but we are not listening on the right frequencies, or we have not been listening long enough. A signal from a civilization 1,000 light years away would have to have been sent in the year 1024 AD for us to hear it now. We have only been listening for a human lifetime. We might be hearing nothing because we have just put our ear to the door. Or maybe they are deliberately staying quiet. The dark forest theory is one reason. Another is the zoo hypothesis. This idea suggests that advanced civilizations know we are here, but they are deliberately avoiding contact. They are observing us like we observe animals in a nature preserve. They do not interfere, allowing our primitive culture to develop on its own. We would be an object of study or entertainment, but never an equal. This is a less terrifying but more humbling idea. We would not be alone, but we would be insignificant. The simplest answer is often the most likely. The simplest answer is that there is no one else, or at least no one else close enough for us to hear. The silence does not have to be a complex puzzle. It might just be the sound of an empty room. This forces us to confront our own solitude. If we are the only thinking beings in this vast expanse, it places an enormous responsibility on our shoulders. The universe becomes a stage, and we are the only actors. All the meaning, all the art, all the discovery would be up to us. The silence might be an answer. It might be telling us that we are on our own. Number 18, the universe should not exist at all. In the first moments of the Big Bang, energy congealed into matter. According to the standard model of particle physics, this process should have created equal amounts of matter and antimatter. For every electron, there should have been a positron. For every proton, an antiproton. When a particle of matter meets its antimatter counterpart, they annihilate each other in a flash of pure energy. If the early universe had perfect symmetry with equal matter and antimatter, everything would have been destroyed. The universe would be empty, it would contain nothing but a sea of leftover photons, but that is not what we see. We live in a universe made almost entirely of matter. Galaxies, stars, planets, and people are all made of matter. Antimatter is incredibly rare. Something happened in that first second of creation. Some unknown process created a tiny imbalance. For every billion particles of antimatter, there were 1,000,000,001 particles of matter. After all the annihilation, that 1 in a billion surplus of matter was left over. That tiny remnant is everything we see today. We are the leftovers of a cosmic war between matter and antimatter. We do not know why this asymmetry exists. It is one of the biggest mysteries in physics. This imbalance, known as baryogenesis, is not predicted by the standard model. Physicists have been searching for the source of this CP violation for decades. Experiments at particle accelerators like CERN are trying to find tiny differences in the way matter and antimatter particles behave and decay. So far, the differences they have found are not nearly large enough to explain the universe we live in. This question goes to the heart of our existence. We are here because of an imperfection, a flaw in the symmetry of creation. If the laws of physics were perfectly balanced, we would not be here to ponder them. This suggests that our existence is contingent on a fundamental cosmic accident. It also connects to another profound problem. Why is there something rather than nothing? This is a question philosophers have asked for centuries. Physics offers a potential, but deeply strange, answer. The total energy of the universe appears to be zero. The positive energy of matter and radiation seems to be perfectly balanced by the negative energy of gravity. The universe, in a sense, is the ultimate free lunch. Quantum field theory tells us that nothing, a perfect vacuum, is not truly empty. It is a bubbling soup of virtual particles and fields popping in and out of existence. It is possible that the entire universe is just one of these fluctuations, a random event that due to its zero energy state could spring from nothing without violating the laws of conservation of energy. But this just pushes the question back a step. Why do those quantum laws exist? Why is there a framework that allows a universe to pop out of nothing? We have no answer. We are faced with a stark reality. The fact that we exist is a profound puzzle. We are made of matter that should have been annihilated. We live in a universe that could have been an empty void. Our presence seems to be the result of a lucky break on a cosmic scale. It forces us to ask if there is some deeper principle at work, or if we are simply the product of a series of fortunate accidents. The universe is not obligated to make sense to us. The fact that it exists and that we are in it is the most fundamental mystery we can contemplate. In number 17, our past might not be gone. The speed of light in a vacuum is 299,792,458 meters per second. It is the cosmic speed limit. Nothing can travel faster. Because of this finite speed, when we look at distant objects in the universe, we are not seeing them as they are now. We are seeing them as they were in the past. The light from the sun takes about 8 minutes and 20 seconds to reach Earth. If the sun were to suddenly disappear, we would not know it for over 8 minutes. The light from Proxima Centauri, the nearest star to our solar system, takes over 4 years to reach us. When we look at that star, we see it as it was 4 years ago. The Andromeda Galaxy is 2.5 million light years away. The light we see from it tonight began its journey when early human ancestors were first walking on the African savanna. Telescopes like the Hubble and James Webb are time machines. They can see galaxies so far away that their light has been traveling for over 13 billion years. We are seeing these galaxies as they were shortly after the Big Bang. This has a strange philosophical implication. If an alien civilization in the Andromeda Galaxy had a telescope powerful enough to see details on Earth, what would they see right now? They would see Earth as it was 2.5 million years ago. They would see a world without cities, without civilization, without us. An alien 65 million light years away would see dinosaurs roaming the Earth. This means that, in a very real sense, the past is not gone. It still exists, encoded in light, traveling outward through the cosmos. Every event that has ever happened on Earth is still visible from somewhere in the universe. Your birth, the signing of the Declaration of Independence, the construction of the pyramids, the extinction of the dinosaurs, all of it is still playing out on a wavefront of light expanding away from Earth at the cosmic speed limit. The past is not an ephemeral memory. It is a physical reality streaming through space. This idea is connected to a concept in physics called the block universe. According to Einstein's theory of relativity, time is a dimension, just like the 3 dimensions of space. Together, they form a 4-dimensional fabric called space-time. In the block universe view, all of time, past, present, and future bit exists simultaneously. The entire history and future of the universe is a single, static, 4-dimensional block. Our perception of time flowing from past to future is just an illusion of our consciousness. The present is just a slice of this block that we are currently experiencing. The dinosaurs are not gone. They are just located at a different coordinate in space-time. This view completely changes our understanding of time, causality, and free will. If the future already exists, are our choices real? Or are we just actors in a pre-written play moving through our scripted roles? Physics does not provide a clear answer. Quantum mechanics seems to introduce genuine randomness and uncertainty into the universe, which might conflict with the idea of a fixed future. The debate between a static block universe and a dynamic, evolving present is ongoing. But the fact remains that our past is physically present in the universe. It is not something that has vanished. It is out there, preserved in light. This forces us to reconsider what now even means. So your now is not the same as the now for someone on Mars or someone in another galaxy. The relativity shows that simultaneity is not universal. There is no single objective present moment for the entire cosmos. There is only what is happening for you right here, right now, and your past a moment ago is already on its way to the stars, becoming a permanent part of the cosmic record. Number 16, reality might be a projection. A hologram is a two-dimensional surface that contains all the information needed to create a three-dimensional image. The holographic principle is a speculative idea in physics that suggests our entire three-dimensional universe might be a projection of information stored on a two-dimensional surface at its boundary. The universe, as we experience it, could be a hologram. The idea originated from the study of black holes. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered that the amount of information a black hole can contain is not proportional to its volume, but to the area of its event horizon, the two-dimensional surface that marks its boundary. This was a shocking result. It was as if the contents of a whole room could be described by the information written on its walls. Physicists Gerard Hooft and Leonard Susskind later extended this idea to the entire universe. They proposed that everything that happens inside a volume of space, including our own 3D world, could be described by a theory operating on the boundary of that space. The reality we perceive, with its three dimensions of space and one of time, could be an emergent property. The more fundamental reality would be a flat, 2D field of information like a cosmic computer chip. This is not just a philosophical concept, it has become a serious tool in theoretical physics. In 1997, physicist Juan Maldacena discovered a mathematical link, a duality between a certain theory of gravity in a 3D volume and anti-de Sitter space, and a quantum field theory on its 2D boundary. This adds CFT correspondence allows physicists to translate very difficult problems in one theory into much simpler problems in the other. It is one of the most celebrated results in modern string theory. While this correspondence applies to a specific type of theoretical universe, not our own, it provides mathematical evidence that a holographic principle could be true. It suggests that the fabric of space-time itself might not be fundamental. The fundamental reality could be made of quantum information. If the universe is a hologram, it would change everything. You know, the tangible, solid world around us would be a kind of illusion. The laws of physics we observe would be expressions of underlying informational processes. It could explain some deep mysteries, like the non-local nature of quantum entanglement, where two particles can be linked instantly over vast distances. In a holographic universe, their separation in 3D space would be an illusion. On the fundamental 2D surface, they might still be right next to each other. This idea also intersects with simulation theory, the hypothesis that our reality is a computer simulation created by a more advanced civilization. If the universe is fundamentally informational, then it is, in a sense, computable. It could be run on some kind of vast computational substrate. The holographic principle provides a potential physical mechanism for how such a simulation could work, with the 3D world being a projection of a 2D information base. We are a long way from proving or disproving the holographic principle. Some experiments are looking for evidence. They are trying to detect a fundamental pixelation of space-time. If reality is a projection from a finite amount of information, then at the smallest possible scales, space should not be smooth. It should be blurry or made of discrete units, like the pixels on a screen. So far, no such evidence has been found, but the search continues. The possibility forces us to ask what is truly real. Is the chair you are sitting on a solid object, or is it a complex projection of bits of information? Are we living in a base reality, or are we the characters in a holographic movie? The cosmos might be far stranger and less solid than it appears. Number 15, we are made of stardust. The elements that make up your body were not created on Earth. The carbon in your cells, the oxygen you breathe, the iron in your blood, none of it is native to this planet. Almost every atom in your body was forged inside a star. The Big Bang, 13.8 billion years ago, produced only the lightest elements, hydrogen, helium, and a tiny amount of lithium. That was the entire periodic table for the first few 100 million years of the universe. The first stars were massive and short-lived. They were made almost entirely of hydrogen and helium. Inside their incredibly hot and dense cores, nuclear fusion began. Hydrogen atoms were fused together to create helium. As the stars aged, they fused helium into carbon, then carbon into oxygen, and so on, creating heavier and heavier elements up to iron. When these massive stars reached the end of their lives, they exploded in brilliant supernovae. These explosions were so powerful, they outshone entire galaxies for a brief time. The explosions did two things. First, the intense energy of the supernova created even heavier elements, like gold, silver, and uranium, which could not be formed in the star's core. Second, the explosion scattered all of these newly created elements across the galaxy. This material, this stardust, then mixed with interstellar gas clouds. Over billions of years, these enriched clouds collapsed under their own gravity to form new stars and new planetary systems. Our solar system formed from one such cloud about 4.6 billion years ago. The Earth, the other planets, and the Sun itself were all built from the recycled remains of long-dead stars. Every element on Earth heavier than hydrogen and helium is a product of this stellar alchemy. That includes the building blocks of life. The carbon that forms the backbone of all organic molecules was made in a star. The nitrogen in our DNA, the calcium in our bones, the potassium in our nerves, all stardust. You are a walking, talking collection of atoms that were once at the heart of an exploding star millions or billions of light years away and billions of years ago. This is not a metaphor, it is a literal scientific fact. We are deeply and physically connected to the cosmos. Our origins are not just terrestrial, they are stellar. This connection is profound. It means that the universe is not just something out there to be observed. We are part of it. The same physical processes that create distant nebulae and spiral galaxies also created us. This realization can be both humbling and empowering. It is humbling to know that our substance is just borrowed material from a vast cosmic cycle of birth and death. But it is also empowering to know that we are part of that grand cycle. The universe is not a sterile alien place. It is our ancestral home. The atoms that make up your hand might have come from dozens of different stars. You are a mosaic of cosmic history. This also has implications for the search for life elsewhere. Since the elements of life, carbon, oxygen, nitrogen, are created in stars and scattered throughout the universe, it is very likely that the building blocks for life exist on countless other worlds. The chemistry of life on Earth is based on the most common ingredients in the cosmos. It suggests that life itself might not be a freak accident, but a natural and common outcome of the universe's evolution. We might be one of many forms of stardust that has woken up and started to look back at the stars from which it came. Number 14, the universe is trying to erase information. In the center of most large galaxies, including our own, lies a supermassive black hole. A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape. Its boundary is called the event horizon. Once something crosses the event horizon, it is lost from the observable universe forever. For decades, this led to a deep paradox in physics, one that threatened the foundations of science. One of the most fundamental principles of physics is the conservation of information. This principle states that information can never be truly destroyed. You can burn a book, but in principle, if you could collect every particle of smoke and ash and measure its properties, you could reconstruct the information that was in the book. The information is scrambled, but not gone. This is a core tenet of quantum mechanics. Black holes seem to violate this principle. When something falls into a black hole, its information appears to be lost forever. In the 1970s, Stephen Hawking showed that black holes are not completely black. They slowly radiate energy known as Hawking radiation and eventually evaporate over immense timescales. But Hawking's calculations suggested this radiation was thermal, meaning it was random and contained no information about what fell in. So when the black hole completely evaporated, the information would be truly and permanently destroyed. This was the black hole information paradox. It created a deep conflict between general relativity, which describes black holes, and quantum mechanics, which demands information is conserved. Physicists have been battling with this problem for nearly 50 years. It forces us to question which of our most fundamental theories is wrong, or at least incomplete. In recent years, a consensus has started to form. Most physicists now believe that information does escape from an evaporating black hole. The solution is likely connected to the holographic principle and the idea that the information is somehow encoded on the surface of the event horizon and imprinted on the outgoing Hawking radiation. The process is incredibly subtle. The correlations in the radiation that carry the information are too complex to ever be decoded in practice, but in principle, they are there. Information is saved, but the struggle with this paradox reveals a deeper truth about the cosmos. The universe seems to have a strange relationship with information. On one hand, the laws of physics are designed to preserve it. On the other hand, powerful cosmic objects like black holes seem purpose-built to destroy it. This connects to the concept of entropy. The second law of thermodynamics states that the total entropy, or disorder, of a closed system always increases over time. A scrambled egg will not unscramble itself. A cup of coffee cools down, its heat dissipating into the room. This arrow of time, this relentless march toward disorder, is a kind of information loss. The ordered state of the egg contains more useful information than the disordered state of the scrambled egg. The ultimate fate of the universe might be a state of maximum entropy, known as the heat death. In this scenario, trillions of years from now, all stars will have burned out, all black holes will have evaporated, and the universe will be a cold, dark, uniform soup of elementary particles. All structure, all complexity, and all information will be gone. So, is information fundamental and eternal, as quantum mechanics suggests? Or is the universe a machine designed for its ultimate erasure, as thermodynamics seems to imply? Our existence as complex, information-rich beings is a temporary rebellion against this cosmic trend toward disorder. We are fleeting patterns of information in a universe that seems determined to smooth everything out into featureless oblivion. The cosmos forces us to ask whether our knowledge, our art, our very consciousness can escape this ultimate fate. Number 13, the laws of physics might not be universal. We assume that the laws of physics are the same everywhere and at all times. The force of gravity on a distant star is governed by the same equations that make an apple fall on Earth. The charge of an electron here is the same as the charge of an electron in a galaxy a billion light years away. This assumption, the cosmological principle, is the bedrock of all modern cosmology. It allows us to study the entire universe using the laws we discover here on Earth. But what if it is not true? What if the laws of physics, or at least the fundamental constants that underpin them, can change in different parts of the universe or have changed over cosmic time? This is a speculative but serious area of research. For decades, scientists have been looking for evidence that the fundamental constants of nature are not, in fact, constant. One of these is the fine structure constant, often called alpha. It is a number, roughly 1/137, that determines the strength of the electromagnetic force. This force governs how atoms hold together, how chemical reactions work, and how light interacts with matter. It is one of the most important numbers in all of physics. Like if it were even slightly different, the universe would be unrecognizable. Stars might not ignite, or carbon atoms might not be stable. Life as we know it would be impossible. In the late 1990s, a team of astronomers studying light from distant quasars found tentative evidence that the fine structure constant might have been slightly smaller billions of years ago. The light from these quasars has traveled for billions of years, so it provides a snapshot of the laws of physics in the distant past. The claim was controversial, and subsequent studies have produced conflicting results. Some support the idea of a changing alpha, while others find no evidence for it. The research is ongoing. If a fundamental constant like alpha could change, it would shatter our understanding of the cosmos. It would mean that the universe is not a single, uniform entity. It could be a patchwork of different domains, each with its own local physical laws. Our observable universe might just be one bubble, where the constants happen to have the values that allow for our existence. This ties into string theory and the concept of the multiverse. String theory suggests that there are extra hidden dimensions of space. The way these dimensions are curled up and configured determines the values of the fundamental constants in our 3D world. The theory predicts a vast landscape of possible configurations, perhaps as many as 10 to the power of 500. Each configuration would result in a different universe with different physical laws. Our universe would be just one of an infinite number of parallel worlds. In this scenario, the laws of physics are not fundamental. They are more like local bylaws set by the specific geometry of space-time in our corner of the multiverse. We find ourselves in a universe where the laws are just right for life because we could not exist in any of the others. This is known as the anthropic principle. This idea is both exciting and frustrating for physicists. It is exciting because it could explain why the constants of nature seem so perfectly fine-tuned for our existence. But it is frustrating because it might be impossible to test. How could we ever get evidence of another universe with different laws? The question challenges our most basic assumptions. We look at the sky and see a universe governed by elegant, unchanging mathematical laws. But this might be a local illusion. The cosmos could be a much wilder, more chaotic place than we imagine, with the rules of the game changing from one place to another. We might just live in a small, comfortable oasis where the laws happen to settle down in our favor. Number 12. Our definition of life is hopelessly limited. When we search for life on other worlds, what are we looking for? Typically, we look for conditions similar to Earth, or we look for rocky planets in the habitable zone of a star where temperatures could allow for liquid water. We analyze atmospheres for biosignatures, gases like oxygen or methane that could be produced by living organisms. We assume that life elsewhere will be, at least in its basic chemistry, like life here. We look for carbon-based organisms that use water as a solvent, but this is an incredibly narrow view. We are basing our entire search on a single data point, life on Earth. It is like visiting one small island, seeing that all the animals have fur, and concluding that all animals in the world must have fur. The universe is vast and strange. Why should we assume that life everywhere must follow our local rulebook? Consider the alternatives. Life on Earth is carbon-based because carbon is an incredibly versatile element. It can form 4 strong chemical bonds, creating the complex chains and rings needed for molecules like DNA and proteins. But silicon sits just below carbon on the periodic table. It can also form 4 bonds. Could there be silicon-based life on a world much colder than Earth, perhaps with a liquid methane ocean instead of water? Silicon-based chemistry might be possible. Such life would be slow, ponderous, and utterly alien. Water is a fantastic solvent for our kind of biology. But it is not the only one. On Saturn's moon Titan, it is so cold that water is frozen as hard as rock. But Titan has rivers, lakes, and seas of liquid methane and ethane. Could these liquid hydrocarbons serve as a solvent for a different kind of life? In 2015, scientists at Cornell University modeled a potential cell membrane that could function in liquid methane. This azotose would be made of nitrogen compounds and would be flexible and stable at Titan's cryogenic temperatures. We assume life needs the energy of a star, but on Earth, we have found entire ecosystems that thrive in complete darkness. Around hydrothermal vents on the ocean floor, bacteria get their energy not from sunlight, but from chemical reactions, a process called chemosynthesis. These bacteria form the base of a food chain that includes giant tube worms, crabs, and fish. Could life exist on a rogue planet, a world ejected from its star system and drifting in the cold darkness of interstellar space? If it had a hot core and a liquid ocean under a thick sheet of ice, it could have all the ingredients for a chemosynthetic ecosystem, completely independent of a star. What about life in more exotic environments? Could life exist in the plasma of a star's corona? Could vast, intelligent clouds of dust and gas form in interstellar space, thinking thoughts on timescales of millions of years? Could life be based on magnetic fields or nuclear forces instead of chemistry? These ideas are highly speculative, but they are not impossible. We simply do not know the limits of what life can be. Our current search strategy is like looking for your keys only under the streetlight, because that is where the light is. We look for water and carbon-based life because that is the only kind we know how to look for. But we might be missing a vast, undiscovered zoo of alien life forms that are right in front of us. The cosmos forces us to be humble about our definitions. Life might not be a single narrow category. It might be a broad spectrum of processes by which matter organizes itself to become complex and replicate. The forms we see on Earth could be just one tiny corner of a vast possibility space. The most profound discovery we could make might not be finding life just like us, but finding life that is so different it forces us to redefine the word itself. Number 11, there could be an infinite number of you. Quantum mechanics, the theory that governs the subatomic world, is famously strange. One of its strangest features is that particles like electrons do not have a definite position or state until they are measured. Before a measurement, they exist in a superposition of all possible states at once. The act of observation seems to force the particle to choose one state. For decades, this was a deep puzzle known as the measurement problem. In the 1950s, a physicist named Hugh Everett III proposed a radical solution. He suggested that the particle does not choose one state. Instead, every time a measurement is made, the entire universe splits into multiple copies. In each copy, one of the possible outcomes becomes the reality. If a particle can be in state A or state B, then after the measurement, there are two universes. In one, the particle is in state A. In the other, it is in state B. This is the many worlds interpretation of quantum mechanics. This idea is staggering in its implications. Every quantum event, from the decay of a radioactive atom to the interaction of photons in your eye, would cause the universe to branch. This would be happening constantly, trillions of times a second, all around us. The number of parallel universes would be incomprehensibly large and growing all the time. In one of these universes, you decided to read this sentence. In another, you stopped reading a paragraph ago. In yet another, you never opened this page at all. Every choice you could possibly make at every moment of your life is made by a version of you in some parallel universe. There is a universe where you took that job you turned down, a universe where you moved to a different country, to a universe where you were born with a different eye color. If the universe is infinite in space, which is consistent with our current cosmological models, then a similar conclusion can be reached without quantum mechanics. In an infinite space, every possible configuration of particles must occur somewhere. And not just once, but an infinite number of times. Far beyond the edge of our observable universe, there would be another region of space identical to ours, and another. There would be an infinite number of Earths, with an infinite number of people identical to you, living out lives that are exactly the same. There would also be infinite worlds where Your life is slightly different and infinitely more where it is wildly different. These two ideas, the quantum multiverse and the cosmological multiverse, both point to the same conclusion: you are not unique. There are countless other versions of you out there. This shatters our sense of self. Is your consciousness the real one? Like, what makes your choices more significant than the choices made by your other selves in other worlds? The many worlds idea is not just science fiction. It is a serious interpretation of quantum mechanics, and it is gaining traction among many physicists because it is mathematically simpler and more elegant than the traditional interpretation, which requires a mysterious collapse of the wave function upon measurement. We have no way to test for these other worlds. By their very definition, they are causally disconnected from our own. We can never visit them or communicate with them, but their potential existence forces a profound philosophical shift. It means that every possibility is realized, nothing is lost, every path not taken in your life is taken by another you. It suggests a kind of conservation of reality where no potential outcome is ever wasted. It also raises disturbing questions. If a version of you in another universe commits a terrible crime, are you somehow connected to that? Or if a version of you achieves great things, does that have any meaning for you? The cosmos might contain not just other worlds, but other yous, and we may never know for sure. Number 10, our sun will die and Earth with it. Our sun is about 4.6 billion years old. It is a middle-aged star, a yellow dwarf. It is currently in the most stable phase of its life, fusing hydrogen into helium in its core. This process has been going on for billions of years, and it will continue for about another 5 billion years. But it will not last forever. The sun, like all stars, has a finite lifespan. Its death will mean the end of the Earth. As the sun runs out of hydrogen fuel in its core, it will begin to change. The core will contract and heat up, causing the outer layers of the sun to expand dramatically. The sun will swell into a red giant. Its surface will grow so large that it will engulf the orbits of Mercury and Venus. It will likely swallow the Earth as well. Our planet will be vaporized. Even if Earth were to somehow survive being engulfed, it would be uninhabitable long before that. As the sun begins to expand, its luminosity will increase. In about 1 billion years, the sun will be about 10% brighter than it is today. This extra heat will be enough to cause a runaway greenhouse effect on Earth. The oceans will boil away. The atmosphere will be stripped into space. Earth will become a barren, scorched rock like Venus is today. All life will be extinguished. After its red giant phase, the sun will shed its outer layers, creating a beautiful, glowing planetary nebula. The core that is left behind will be a white dwarf, a super dense object about the size of the Earth. It will be incredibly hot, but it will no longer have any nuclear fusion to power it. It will slowly cool down over trillions of years, eventually becoming a cold, dark, black dwarf. That will be the final gravestone of our solar system. This is not a possibility. It is a certainty dictated by the laws of stellar evolution. We know this is our planet's fate. The timescale is immense, far longer than the entire history of our species. But it is finite. Our world has an expiration date. This forces us to confront our own impermanence on a cosmic scale. Humanity cannot stay on Earth forever. If our species is to survive in the long term, we must eventually leave our homeworld and travel to other stars. This is the ultimate motivation for space exploration. It is not just about curiosity or adventure, it is about survival. The challenges are enormous. The nearest star is over 4 light years away. With our current technology, it would take tens of thousands of years to get there. We would need to develop new forms of propulsion, perhaps using fusion rockets or light sails. We would need to build generation ships, self-sustaining habitats that could support a human population for centuries. We would need to learn how to create stable ecosystems in deep space. Even if we succeed, it will not be a permanent solution. The universe itself has a lifespan. Stars will eventually burn out, galaxies will drift apart. The universe is expanding, and the expansion is accelerating trillions of years from now. Every galaxy will have moved so far away from every other galaxy that they will be beyond the cosmic horizon. An observer in a future galaxy would look out and see nothing but empty space. The universe will become a collection of dark, isolated islands. This process will culminate in the heat death of the universe, a state of maximum entropy where no work can be done. It will be a cold, dark, and empty void. This seems to be the ultimate fate of everything. The cosmos forces us to think on these vast timescales. Our lives are a brief flash. Our civilization is a momentary flicker. Even our planet and our star are temporary. We are part of a story that is much, much larger than ourselves, a story that has a beginning, a middle, and a definitive end. What we do in our short time on this stage is up to us. Number 9, dark matter and dark energy are the real universe. Everything we can see in the universe, the stars, the galaxies, the planets, the gas clouds is made of normal baryonic matter. It is the matter that makes up you, me, and everything we have ever touched or studied. For most of human history, we assumed that this was all there was. We were wrong. All of the visible matter in the cosmos accounts for less than 5% of its total mass and energy. The other 95% is a complete mystery. About 27% of the universe is something called dark matter. We know it exists because we can see its gravitational effects. In the 1930s, astronomer Fritz Zwicky observed that galaxies in the Coma cluster were moving too fast. There was not enough visible matter in the galaxies to provide the gravitational pull needed to hold the cluster together. It should have flown apart. Zwicky proposed that there was some kind of invisible dunkel materie or dark matter providing the extra gravity. His idea was ignored for decades. But in the 1970s, astronomer Vera Rubin found even more compelling evidence. She studied the rotation of individual spiral galaxies. She found that stars on the outer edges of the galaxies were moving just as fast as stars near the center. This defied Newtonian physics. If the visible matter was all there was, the outer stars should have been moving much more slowly. The only explanation was that the galaxies were embedded in a vast, invisible halo of dark matter, which provided the extra gravity. Today, the evidence for dark matter is overwhelming. We see its effects in the way light from distant galaxies is bent by gravity, a phenomenon called gravitational lensing. We see it in the structure of the cosmic microwave background, the afterglow of the Big Bang. We know dark matter is there, but we have no idea what it is. It does not interact with light or any other form of electromagnetic radiation, which is why it is dark. It does not seem to interact with normal matter either, except through gravity. Billions of dark matter particles are probably streaming through your body right now, and you do not feel a thing. And scientists are running huge experiments deep underground, trying to get a dark matter particle to bump into a nucleus of normal matter, but so far they have found nothing. It is one of the most profound and embarrassing gaps in our knowledge. The other mystery is even bigger. About 68% of the universe is something called dark energy. In the late 1990s, 2 teams of astronomers were studying distant supernovae to measure the expansion rate of the universe. They expected to find that the expansion was slowing down due to the pull of gravity. Instead, they found the exact opposite. The expansion of the universe is accelerating. It is speeding up. To explain this, cosmologists proposed the existence of a mysterious force, a kind of anti-gravity that is pushing space-time apart. They called it dark energy. It seems to be a property of space itself. As space expands, more dark energy is created, which causes the expansion to accelerate even more. We know even less about dark energy than we do about dark matter. It is a placeholder name for our ignorance. This means that we are living in a universe that we do not understand. The vast majority of reality is made of substances and forces that are completely invisible and unknown to us. The 5% of the universe that we can see and study is just the foam on the top of a deep, dark, cosmic ocean. This is a deeply humbling realization. All of our science, all of our philosophy, all of our understanding is based on a tiny fraction of what is actually out there. We are like ancient map makers drawing detailed charts of our own little island, completely unaware of the vast continents that lie across the sea. The cosmos is not just bigger than we thought, it is fundamentally different. It forces us to acknowledge the profound limits of our perception and knowledge. The real universe is still waiting to be discovered. Number 8. Consciousness might be a fundamental property of the universe. What is consciousness? What is the nature of subjective experience? How does the gray, jelly-like matter of the brain produce the rich inner world of thoughts, feelings, colors, and sounds? This is known as the hard problem of consciousness. We can map the neural correlates of conscious experience, seeing which parts of the brain light up when you see the color red. But we have no idea how or why that physical process creates the subjective feeling of redness. The conventional scientific view is that consciousness is an emergent property. It arises from the complex processing of information in the brain. It is something that happens when a system, like a neural network, reaches a certain level of computational complexity. In this view, consciousness is a late arrival in the universe, limited to a few species with advanced brains on one small planet. But there is another more ancient and radical idea, panpsychism. Panpsychism is the view that consciousness is not a special property of brains, but a fundamental and ubiquitous feature of the universe. In this view, all matter has some form of consciousness, or at least a primitive precursor to it. An electron, a rock, a star, they do not have consciousness in the complex, self-reflective way a human does. But they have some rudimentary form of raw, subjective experience. This might sound strange, but it is taken seriously by a number of philosophers and neuroscientists. They argue that it is the most elegant solution to the hard problem. If consciousness is fundamental, then we do not have to explain how it mysteriously pops into existence from non-conscious matter. Instead, the challenge is to explain how these primitive bits of microconsciousness combine to form the macro-consciousness that we experience. This is the combination problem. How would this work? One idea, championed by neuroscientist Giulio Tononi, is integrated information theory 2T. This theory proposes that consciousness is a measure of a system's integrated information. Any system that has a certain degree of complexity and in which information is highly interconnected will have some level of consciousness. This would apply to brains, but it could also apply to other systems like complex computer networks or perhaps even physical systems on a cosmic scale. Could a star be conscious? Could a galaxy have a form of collective consciousness that operates on billion-year timescales? From a panpsychist perspective, this is not impossible. The universe is a vast, interconnected network of matter and energy. It is constantly processing information. Perhaps the universe as a whole possesses a form of consciousness that is far beyond our comprehension. This idea resonates with some of the deepest spiritual traditions in human history, which often speak of a universal mind or a cosmic consciousness. While panpsychism is a philosophical and scientific theory, not a spiritual one, it points to a similar conclusion: our individual consciousness is not an isolated phenomenon. And it is a manifestation of a property that is woven into the fabric of reality itself. This would fundamentally change our place in the cosmos. We would not be lonely, thinking specks in a dead, unfeeling universe. We would be part of a universe that is, in its very essence, experiential. The cosmos would not just be something we observe from the outside. We would be a part of its own process of self-awareness. We are a very long way from knowing if this is true. But the hard problem of consciousness is so difficult that it forces us to consider such radical possibilities. The universe looks at us through our eyes. Maybe, in some way we do not yet understand, it is also looking at itself. Number 7. The universe seems fine-tuned for our existence. The laws of physics are described by a set of fundamental constants. These are numbers like the strength of gravity, the mass of the electron, and the speed of light. These numbers are not derived from any theory. They are measured values. We have to plug them into our equations by hand. And they have a very strange property. If you were to change the value of any of these constants by even a tiny amount, the universe would be a sterile and lifeless place. Take the strong nuclear force, the force that binds protons and neutrons together in an atomic nucleus. If it were just 2% stronger, all the hydrogen in the early universe would have been rapidly fused into heavier elements. There would be no hydrogen left to form stars like our sun, and no water. If it were 2% weaker, protons could not stick together and only hydrogen would exist. No other atoms, no chemistry, no life. Or consider the force of gravity. If it were slightly stronger, stars would burn out much faster, not giving life enough time to evolve. The universe might have collapsed back on itself long ago. If it were slightly weaker, stars and galaxies would never have formed in the first place. The universe would be a thin, uniform soup of gas. The expansion rate of the early universe, driven by dark energy, is another example. If it had been a tiny fraction smaller, the universe would have recollapsed into a big crunch. If it had been a tiny fraction larger, it would have expanded so fast that galaxies and stars never had a chance to form. The precision required is like balancing a pencil on its tip for 14 billion years. This is the fine-tuning problem. The universe appears to be balanced on a knife's edge for the existence of life. There are 3 main explanations for this apparent cosmic coincidence. The first is pure chance. Maybe we just got incredibly lucky. The universe just happened to have the right numbers for us to exist. This is possible, but it strikes many scientists as deeply unsatisfying. It is like surviving a firing squad of 1 million skilled marksmen and concluding that they all just happened to miss by chance. The second explanation is a creator. The fine-tuning could be evidence of a deliberate design. A cosmic intelligence could have, set the dials of the physical constants to the exact values needed to allow for conscious beings to emerge. This is a theological explanation, and it lies outside the realm of what science can test. The third explanation, and the one favored by many physicists, is the multiverse. As we discussed before, if there is a vast, perhaps infinite, number of other universes, each with its own randomly set physical laws, then it is no longer surprising that we find ourselves in one that is hospitable to life. We could not exist in any of the others to observe them. This is the anthropic principle. We are here because we are here. The fine-tuning is a selection effect. We are observing the universe that was able to produce observers. Each of these explanations is profound. If it is chance, then our existence is a staggering fluke, a precious and improbable accident. If it is design, it changes the entire relationship between science and religion. If it is the multiverse, it means that our reality is just one of countless others, and our seemingly special laws are just a local environmental condition. The cosmos forces this question upon us. We are confronted with the apparent fact that the universe is built in a way that allows us to be here. Is this a sign of purpose, a lucky roll of the cosmic dice, or evidence of a reality far vaster than we can see? We do not have the answer, but the question itself redefines our place in the universe. Number 6, time may not be real. Our entire experience of reality is built on the passage of time. We remember the past, we experience the present, and we anticipate the future. Time feels like a fundamental force, a river that carries us inexorably forward. But what if this is all an illusion? What if time, as we perceive it, does not actually exist? This is a serious proposition in theoretical physics. The problem is that our two best theories of the universe describe time in completely different ways. In quantum mechanics, time is a background parameter. It is a universal clock that ticks away, the same for everyone. It is the stage on which the quantum drama unfolds, but in Einstein's theory of general relativity, time is not absolute. It is part of the fabric of space-time, and it is relative. Time can be bent and warped by gravity. A clock on a mountaintop ticks faster than a clock at sea level. A clock on a fast-moving spaceship ticks slower than a clock on Earth. There is no single universal now. This conflict becomes a crisis when physicists try to unite the two theories into a single theory of quantum gravity. In many of these attempts, like the Wheeler-DeWitt equation, the variable for time simply disappears from the equations. The most fundamental description of the universe seems to be timeless. This suggests that time is not a fundamental aspect of reality. It is an emergent property. It is something that appears at our macroscopic level in our thermodynamic and psychological world, but does not exist at the most basic quantum level. So where does our sense of time come from? One idea is that it is connected to entropy. The second law of thermodynamics says that disorder always increases. This gives time a direction, an arrow. We remember the past because it was a state of lower entropy. We do not remember the future because it has not yet settled into a definite state. Our minds, as information processing systems, are tied to this thermodynamic arrow. Another idea is that time is a product of our consciousness. Our brains construct a narrative of events, a sequence of cause and effect, to make sense of the world. The flow of time might be a feature of our perception, not a feature of the universe itself. This aligns with the block universe idea, where past, present, and future all exist simultaneously, and our consciousness simply illuminates one frame of the cosmic movie at a time. This is a deeply counterintuitive concept. It goes against our most basic experience. But the cosmos often does that. If time is not real, it changes everything. The concepts of beginning and end become meaningless. The Big Bang would not be the start of time, but just a particular configuration in the timeless block of reality. The future would not be an unknown territory we are heading into, but a landscape that already exists. It also changes our understanding of mortality. If all moments exist forever, then the moments of your life are not lost to the past. They are permanently etched into the fabric of space-time. The people you have loved and lost are not gone. Well, they are just located at a different coordinate in this timeless reality. The cosmos forces us to question our most fundamental assumption. The clock on the wall, the turning of the seasons, the feeling of moments slipping away, all of it might be a grand illusion. The true nature of reality might be static, eternal, and timeless. Number 5, we are cosmic sensors. The universe is governed by physical laws. These laws appear to be consistent and predictable, but they also have strange limits. One of these is the cosmic censorship hypothesis, a principle proposed by physicist Roger Penrose. It states that the universe hides its most extreme and bizarre phenomena from us behind a veil of cosmic censorship. The phenomena in question are singularities. A singularity is a point in space-time where the laws of physics, as we know them, break down. Density, gravity, and the curvature of space-time become infinite. General relativity predicts that singularities exist at the center of every black hole, and that the universe itself began with a singularity in the Big Bang. A singularity is a place where predictability ends. If you could see a singularity, you could see a place where anything is possible, where cause and effect cease to have meaning. It would be a hole in the fabric of reality. According to the cosmic censorship hypothesis, the universe does not allow this. It states that every singularity must be hidden behind an event horizon. This is why black holes are the perfect cosmic sensors. The singularity at the center is real, but it is forever concealed from the outside universe by the event horizon. We can never see it, study it, or be affected by its lawless nature. The universe protects the integrity of its laws by quarantining its own breakdowns. What if this hypothesis is wrong? A singularity that is not hidden behind an event horizon is called a naked singularity. If naked singularities could exist, they would be the most bizarre objects in the universe. They would be points of infinite density and gravity, visible to anyone. They would be places where information could be created or destroyed, where the future could not be predicted from the past. A spaceship flying near a naked singularity might be transformed into a teapot or a shower of gold coins for no reason at all. The universe would become chaotic and unpredictable. So far, all our observations are consistent with cosmic censorship. We have never seen evidence of a naked singularity, but some theoretical models suggest they might be possible under very specific conditions, for example, with a rapidly spinning black hole. This principle forces us to ask a strange question. Is the universe intentionally hiding its own secrets? The laws of physics seem to have a built-in mechanism to prevent us from seeing the places where those very laws fail. It is as if the operating system of the universe has firewalled its own corrupted files. This connects to a deeper philosophical idea. Perhaps our perception of an orderly, lawful universe is itself a form of censorship. Our brains and our scientific instruments are evolved and designed to perceive a certain slice of reality. We see a world of stable objects, cause and effect, and linear time, but this might be a filtered version of a much stranger and more chaotic underlying reality. Quantum mechanics hints at this. At the subatomic level, the world is not orderly and predictable. It is a fuzzy, probabilistic dance of potential. It is only when we observe it, when we censor it with our measurement, that it resolves into a single classical reality. The cosmos might be a far more magical and less lawful place than it appears. The consistency we observe might be a feature of our limited perspective. We might be living inside a cosmic censorship field, a bubble of order in a sea of potential chaos. The universe might not just be hiding singularities. It might be hiding its true nature from us. Number 4, mathematics is unreasonably effective. In 1960, the physicist Eugene Wigner wrote a famous paper called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. He was marveling at a profound mystery. Why is it that the universe can be described so perfectly by abstract mathematical concepts? Why do equations developed in a mathematician's mind with no thought for the real world turn out to be the exact language needed to describe the behavior of planets, particles, and galaxies? For example, when Einstein was developing his theory of general relativity, he used a form of abstract geometry developed by Bernhard Riemann in the 19th century. Riemann had no idea his work would one day be used to describe the force of gravity. He was just exploring the logical possibilities of curved spaces, yet his mathematics was the perfect tool for the job. The same is true for quantum mechanics, which is built on the abstract mathematics of Hilbert spaces and group theory. There is no logical reason why this should be the case. The universe does not have to be mathematically comprehensible to us. It could have been a chaotic mess, or it could have been governed by principles that are totally alien to our mathematical way of thinking. Yet, we find that it is deeply and elegantly mathematical. There are two main schools of thought on this mystery. The first is Platonism. This is the idea that mathematical objects, numbers, shapes, equations are not human inventions. They are real entities that exist in some abstract, non-physical realm. Mathematicians do not invent math, they discover it. The universe is mathematical because it is built according to this pre-existing mathematical blueprint. The physical world is just a shadow or an imperfect copy of this perfect mathematical reality. In this view, a physicist is like a biologist studying a new species. They are discovering the properties of something that already exists. The other view is formalism or anti-realism. This is the idea that mathematics is a human invention. It is a formal language we created with rules and axioms that we made up. It happens to be a very useful tool for describing the universe, but it does not have any independent reality. The reason it is so effective is because our brains, and therefore our mathematics, evolved in this universe. We have developed a way of thinking that is good at modeling the patterns we see around us. We are imposing our mathematical structures on the world, not discovering them in it. The debate is not settled, but the question is profound. Is the universe itself mathematical? Or is mathematics just the best language we have found to talk about it? If Platonism is right, it means that there is a layer of reality that is more fundamental than the physical world we see. It would mean that abstract truths are not just in our heads, but are woven into the fabric of existence. It would also suggest that an advanced alien civilization would likely discover the same mathematical principles because they are universal truths. If formalism is right, it is a testament to the power of the human mind. It would mean that we have created a system of thought so powerful that it can unlock the secrets of the cosmos. But it might also mean that our understanding is limited by our human-centric way of thinking. An alien species might have a completely different, non-mathematical way of understanding the universe that is just as valid, or even more powerful. The cosmos forces us to wonder about the nature of truth itself. When we write down an equation that perfectly predicts the motion of a planet, are we reading the mind of God as Kepler believed? Or are we just getting very good at a game that we invented ourselves? Number 3. The end of the universe is the end of meaning. The universe had a beginning. As far as we know, it will also have an end. The most likely scenario, based on our current understanding of dark energy, is the heat death. This will happen on a timescale almost too large to comprehend. In about 100 trillion years, the last star will flicker and die. The universe will go dark. For a time, the cosmos will be populated by the dead remnants of stars, black dwarfs, neutron stars, and black holes. Over even longer timescales, on the order of googles of years 10 to the power of 100, these objects will also decay. Protons may decay, causing all matter to dissolve into a thin soup of radiation and particles. And black holes will slowly evaporate through Hawking radiation. Eventually, after a truly unimaginable length of time, the universe will approach a state of final equilibrium. It will be a cold, dark, empty void with particles and photons spread so thinly that they will almost never interact. It will be a state of maximum entropy. No work will be possible. No change will occur. The universe will be, for all practical purposes, dead. This is the ultimate fate that our science predicts. A universe that began in a fiery burst of creation will end as a silent, frozen tomb. This cosmological endpoint forces us to confront a difficult philosophical question. If everything is destined for oblivion, what is the meaning of anything we do? All of our struggles, our achievements, our art, our love, our knowledge, all of it will be erased. The works of Shakespeare, the theories of Einstein, the memories of your life, they will all be lost as if they never existed. The information that constitutes humanity will be scattered and destroyed by the relentless increase of entropy. In the final state of the universe, there will be no memory that we were ever here. Does this cosmic pessimism render our lives meaningless? Some philosophers, like the existentialists, would say no. They would argue that we must create our own meaning in the face of a meaningless universe. The value of our actions is not in their permanence, but in the fact that we choose to do them here and now. The beauty of a sunset is not diminished by the fact that it is temporary. The meaning of a human life is not erased by its finite span. Others might find this a bleak and terrifying prospect. It suggests that the universe has no inherent purpose or direction. We are just a brief, accidental flicker of complexity in a cosmos that is indifferent to our existence and is destined for ultimate simplicity and death. This question also drives some speculative far future physics. Could a sufficiently advanced civilization find a way to escape the heat death? Could they harness the energy of black holes to power their civilization for trillions of years? Could they create baby universes in a lab and escape into a new creation? Could they find a way to store information in a form that could survive the final decay of matter? These are wild ideas, but they are born from a deep human desire to find meaning and permanence in a transient universe. The cosmos presents us with a paradox. It is a place of incredible beauty, complexity, and wonder. It has produced beings who can ponder their own existence, and yet it seems to be heading toward a state where all of that will be annihilated. The final state of the cosmos forces us to look inward. If there is no ultimate external meaning provided by the universe, then the meaning of our lives must be found within our lives themselves. It must be found in our connections to each other, in our pursuit of knowledge, and in our appreciation of the brief, beautiful moment we have in the light before the long cosmic night falls. Number 2, we don't know where the edge of the universe is. What is the universe expanding into? When we hear that the universe is expanding, we tend to picture a balloon being inflated. The galaxies are like dots on the surface of the balloon, and as it inflates, they all move away from each other. But this analogy has a major flaw. A balloon is expanding into the space around it. The universe is not. The expansion of the universe is the expansion of space-time itself. It is not expanding into some pre-existing empty void. The universe is, by definition, everything there is. There is no outside to the universe. This is a concept that is very difficult for our minds to grasp, as we are used to thinking of things existing within a larger space. This leads to the question of whether the universe is finite or infinite. Our current observations cannot answer this. We can only see a finite part of the universe, the observable universe. This is a sphere with a radius of about 46.5 billion light years. This is the distance that light has had time to travel to us since the Big Bang. We have no idea what lies beyond this cosmic horizon. There are 3 possibilities for the overall shape or topology of the universe. It could be flat, like a sheet of paper. It could be closed, like the surface of a sphere. Or it could be open, like the surface of a saddle. Our best measurements from the cosmic microwave background show that the universe is very, very close to flat. If the universe is perfectly flat or open, then it is most likely infinite in extent. It goes on forever in all directions. In this case, our observable universe is just one tiny patch of a much larger infinite reality. If the universe is closed, then it is finite but has no edge. It is like the surface of a sphere. If you travel in a straight line, you will never reach a boundary. You will eventually end up back where you started. In this case, the universe would have a finite size and a finite amount of matter and energy. We do not know which of these is correct, and we may never know. We are trapped within our cosmic horizon. We can never receive any information from beyond the edge of our observable universe. This forces us to confront the limits of our knowledge in the most fundamental way. We do not know the ultimate size or shape of our own home. We are like ancient sailors on a vast ocean, with no idea if the ocean has a shore or if it goes on forever. The concept of an infinite universe is particularly mind-boggling. As discussed before, if the universe is infinite and filled with matter, then every possible configuration of particles must exist somewhere. There would be infinite copies of you, your life, and every possible variation of your life. Every story, every dream, every possibility would be physically realized somewhere in this infinite expanse. The idea of a finite, closed universe is also strange. What does it mean for space to curve back on itself? What determines its overall size? The cosmos forces us to accept that there are some questions we may never be able to answer. We can build powerful telescopes and develop elegant theories, but we may always be limited by our local perspective. We are inside the system we are trying to study. We cannot step outside to get a better look. We are left with a sense of profound mystery. We live in a cosmos whose fundamental properties, its size, and its ultimate boundaries are unknown to us. We are adrift in a reality whose full extent we cannot even imagine. Number one, why is there something instead of nothing? This is the most fundamental question of all. It is the question that lies beneath every other question about the cosmos. Why does anything exist? Why is there a universe with its laws, its matter, its energy, its consciousness? Why is there not just a complete and total void? This is not just a scientific question. It is a philosophical and metaphysical one. Science can describe how the universe evolved from the Big Bang. It can describe the laws that govern its behavior, but it cannot explain why those laws exist or why there was a Big Bang in the first place. Some physicists have tried to offer a scientific answer. As mentioned before, the total energy of the universe appears to be zero, with the positive energy of matter balanced by the negative energy of gravity. This means the universe could have been created from nothing without violating the laws of energy conservation. A quantum fluctuation in a pre-existing vacuum could have given rise to everything we see. The universe could be the ultimate free lunch, but this just pushes the question back. Why do the laws of quantum mechanics exist? What is the nothing from which the universe fluctuated? A quantum vacuum is not true nothingness. It is a complex entity, a sea of virtual particles and fields. It is a something. So the question remains, why is there a quantum vacuum with the potential to create a universe instead of just? He argued that there must be a reason or an explanation for everything that exists. For the universe as a whole, he argued, the sufficient reason must lie outside the universe in a necessary being that we call God. This is a classic theological argument. The existence of the cosmos points to a creator who is the ultimate answer to the question why. Another possibility is that the question itself is flawed. Some philosophers like Ludwig Wittgenstein have argued that it is a meaningless question. Nothing is not a state that can exist. It is just the absence of something. To ask, why is there something, is a misuse of language, like asking, what is north of the North Pole? The universe simply is. There is no why. It is the ultimate brute fact, the starting point for all other explanations. This is a deeply unsatisfying answer for our curious minds. We are wired to seek explanations. To be told that the ultimate reality has no explanation at all feels like a profound intellectual surrender. The cosmos forces us to the edge of reason. We can follow the chain of why questions back through biology, to chemistry, to physics, to cosmology. Why are we here? Because of evolution. Why is evolution possible? Because of chemistry. Why does chemistry work? Because of physics. Why are the laws of physics the way they are? Because of the conditions of the Big Bang. Why was there a Big Bang? And here, the chain breaks. We have no further answer. We are left in silence, staring at the ultimate mystery. This final question contains all the others. The existence of the universe is the precondition for its fine-tuning, for its consciousness, for its beauty, and for its eventual end. It is the one question that science may never be able to answer, and it is the question that makes our brief existence in this vast, improbable, and beautiful cosmos so miraculous and so precious. We are the part of the universe that can ask the question of its own existence, and that in itself is the most astonishing thing of all.